Hello everyone. In this video we will do some examples for comparison tests for improper integrals. Well, recall that by comparison test we mean that we have two functions such that f is less than equal to g and both of them being positive on the interval a to plus infinity. Then if the integral of the smaller function is divergent, then integral of bigger function is going to be divergent. 2 is that if the integral of the bigger function is convergent, then it will force the smaller one has an integral which is convergent. Well, most of the time we are going to be given one function and the other function we have to find depending on our original function. One of the important families that we can always try to compare, and in these examples we will use only that family, it's called p integrals. The integrals which are the form a to infinity for some a positive, 1 over x to the power p dx. So these we know that are convergent, so convergent only by looking at the power of x in the denominator if and only if p is bigger than 1. So if it is 1 or less than 1, the integral is going to be divergent. Okay, let's see the examples here. So we have this strange rational function and we want to see if the improper integral of that is convergent or not. Okay, well, don't try to evaluate that one because that's something out of scope for us. But what we can see here that x to the power 5 plus 6x to the power 4 plus 2x cubed plus x squared plus x plus 7, all these terms for all the values which are bigger than equal to 0, well, we only need bigger than equal to 5, this part is always positive. The last term is also positive, but I need the last term to keep the last term, meaning that adding that to x to the power 5 always will get us a bigger number. Okay, now if we invert both sides, first of all, the inequality will turn around and we will have okay, now our function, the given function, is now there. And it is a function less than another function. And the other function, if you look at the integral of the other function from 5 to infinity, this is indeed a p function, p integral, with p equal to 5, which is bigger than 1. So that as a result, this is a convergent integral. So we had a function bigger than our given function. Our function also was positive. Also, we showed that the bigger function has a convergent integral. So as a result, by comparison test, for improper integrals, integral from 5 to infinity of our function is going to be convergent. without integrating or going into any trouble of doing anything with that rational function. We were able to just use improper integral, the comparison test, and prove that our given integral is convergent. Let's do another example here. Ln of x to the power 2 over root x. You might be able to integrate this one if you know a few tricks here, but indeed you don't need to be able to do that. What you need to know here is that, okay, see, we are working with x is bigger than e, as it is. And if you take ln of e, since ln is increasing function, that will keep the inequality the same way. But ln of e is 1, yes? So as a result of this, we have 1 is less than ln x. Also, you square it still will get bigger number, yeah, bigger than 1. Why I'm doing all this thing? Because I want to generate our function. Now, if I divide both sides by root x, I have generated the inequality. So the lower function here is 1 over root x. The upper function is our function. So this will be something interesting if the lower function has an divergent improper integral. So now note that integral of f of x dx going from e to plus infinity, which is going 1 over root x dx going from e to infinity, which is the same thing as x to the power half dx. This is p integral with p equal to 1 over 2. And since it is less than 1, then you can conclude that the given integral is divergent. So now we have our function bigger than a p integral, which is divergent. So by the comparison test, our integral is going to be a divergent integral. And well, we didn't do anything with that, just showed that we can compare it to a function which is divergent and it's less than this. So that way we proved using comparison test. Let's do one more example. Integral of 4 plus cosine squared over x to the power 4. Here we can use always, you always start cosine, sine is between 1 and 1, but when you square it, it is going to be bigger than 0 and less than 1. If you add 4 to both sides or all sides, you will get this thing, 5. And then you divide all sides by x to the power 3, x to the power 3. Now, the point here is that now I found two functions. One is less than, one is bigger than. Both of them are multiple of 1 over x to the power 3, yes? So which one I should keep? Which one should I use for the comparison test? If you're going to use the upper one, that should be a convergent. If you're going to use the lower one, it should be divergent. Okay, so let's just for a second, you see that both of these guys are multiple of this one, but this is p integral with p equal to 3, which is bigger than 1. So this is convergent, well, going from 1 to infinity. since this is convergent, so it is better to keep it as upper function so that the comparison test works nicely. So just ignore this lower part there, and then you see that now we have gx, our original function is fx, so that is the inequality we have. Then by the comparison test, integral 1 to infinity of 4 plus cosine squared x to the power 3 dx is convergent as well. Well, there was something here. Why didn't you use I5 there? Well, if you multiply that by 5, the convergency don't change. The number would change, will be multiplied by 5, but if it is convergent, it will stay convergent. And that's the only thing we need here. Okay, so these were examples that you can compare the given integral or integrand with a p integral, and then use comparison test and prove that the integral is either divergent or convergent.